here we are to find the real zeros of 4x cubed minus 14x squared plus 25. The possible rational zeros this time are going to be in the form P over Q, where the options for the numerator have to be factors of the constant term 25, so 1, 5, and 25, whereas the options in the denominator have to be divisors of 4, the leading term, so 1, 2, and 4. So this gives us plus or minus, I'll divide by the 1 first, 1, 5, 25, then by the 2, 1/2, 5 halves, 25 halves, and finally by the 4, 1/4, 5/4, and 25/4. So let's look at the graph in this case. I've entered the function into the y equals screen. The largest zeros for rational zeros are plus and minus -25. So let's go into the window and let's use -30 to 30 to start with. And the zeros are all very close to the y-axis. And so let's change our x-min and x-max. Let's do maybe plus and minus 6. For x-min, let's go -6 and x-max 6 and regraph. All right. So we have a 0 of multiplicity 1 on the left side of the y-axis, and possibly a 0 with multiplicity 2 on the right side. Let's come in a little bit more. Let's do x-min and x-max -3 and 3. And let's make our y-min and y-max smaller. I am suspicious that that is not a root of multiplicity 2 on the right, but 2 zeros that are very close together. So let's go for y-min to -1 and y-max to 1. And that is the truth, that there are 2 zeros to the right of the y-axis. Now, what those positive zeros are, I am not certain of. It looks as if we may have a 0 at x equals maybe 2.5. That is one of the options that we have. In order to see that a little bit better, let's just get very close to those zeros on the right. And let's go from, say, x min of 0 up to x max of 3 and see what they look like. And I'm going to think that is a 5/2 or 2.5 as one of those zeros. And so let's go back and check out that conjecture. By using 5/2 as a divisor, and then we've got a missing x term, so we need to remember to put in a coefficient of 0. So we've got 4, -14, 0, and 25. The leading coefficient in the quotient will be 4. 4 times 5/2 is 10. 10 plus -14 is -4. Times -5/2, we'd have -2 times 5, so -10. Adding 0, we'd still have -10. -10 times 5/2 would give -5 times 5, or -25. So that was a correct conjecture that there was a 0 at 2.5 or 5/2. I suspect that the other two zeros may be irrational, or they may be rational from our list of possible rational zeros. In any case, our quotient here is a quadratic. 4, -4, -10 represents the factor 4x squared minus 4x minus 10. So let's apply the quadratic formula with a equal 4, b equals -4, and c equals -10 to find out what our other two zeros are, or other two real zeros are, since we have 3x intercepts. So the opposite of b is 4, plus or minus the square root of 4 squared is 16, minus 4ac all over 2a, which is 8. So this is going to give us 4 plus or minus the square root of 16 plus 160 all over 8. 4 plus or minus the square root of 176 all over 8. Now looking back here, I see that 16 is a factor of both of the terms under the radical. So we're going to be able to factor out a square root of 16 here, which will be a 4. So we'll get 4 plus or minus 4 times the square root. I think it's 11 all over 8. 11 times 16 is 176. So we can factor a 4 out of the numerator. And the 4 cancels with 4 in the denominator. So we get 2 irrational zeros, 1 plus and minus square root of 11 over 2. So our actual zeros, there are 3 of them, 5 halves, and 1 plus or minus square root of 11 over 2. Now, you can find a numerical value for 1 plus the square root of 11 over 2 and 1 minus the square root of 11 over 2. But those would just be approximations to the actual zeros. Sometimes, however, those approximations are useful when you go back and refer to the graph in the relative locations of those x-intercepts.